Now in this lecture we'll answer two questions. On both questions we'll find out the area of the shaded region. So we'll start with the first question. In the drawing we have three semicircles. This is the big semicircle that contains those two smaller semicircles. You know that the radius of this semicircle equals to 2 units in its length. The radius of this semicircle equals to 1 unit in its length. Again, our task is to find out the size of this shaded area. So first of all, we define the center of this semicircle. This point is point P. We define the center of this small semicircle. This point is point Q. We define the point of tendency of tangent AB with this semicircle. This point is point M. And we define the point of tendency of tangent AB with this small circle. This point is point N. Likewise, we define the center of this biggest semicircle. This point is point O. So here we can implement rule 1. We have the radius Pm that equals to 2. The radius Pm is drawn to point M, that is the point of tendency of tangent AB with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MP. If AB is perpendicular to MP, it means that this angle equals to 90 degrees. This angle also equals to 90 degrees according to rule 1. Likewise, the radius Qn that equals to 1, the radius Qn is drawn to point N, that is the point of tendency of tangent AB with this semicircle. Whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NQ. If AB is perpendicular to NQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule, rule 1. Those two small semicircles touch each other externally in this point. So we define the touching point. This point is point T. And whenever you have an external mass between two circles or semicircles like here, you can implement rule 10. So we can click on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes for their touching point. In the drawing, those two circles touch each other externally at this point, point P. The center of this circle is here at point O. The center of this circle is here at point M. The straight line that connects the centers together is of course the straight line OM. According to this rule 10, the straight line OM must pass for the touching point, that is point P. Or OPM is one straight line. Again, OPM is one straight line according to this rule 10. We can actually implement rule 10 in our drawing. Because in our drawing, those two semicircles touch each other externally at point T. The center of this semicircle is here at point P. The center of this small semicircle is here at point Q. The straight line that connects the centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass for point T, that is their touching point. Or PTQ is one straight line. Again, according to rule 10, PTQ is one straight line. So we join points P and Q together by straight line. And the straight line PQ must pass for point T, that is their touching point according to rule 10. we see that indeed the side line PQ passes for point T, that is the touching point, exactly according to rule 10. So in the next step, I copy quadrilateral PQ and M in a new page and we'll do a construction in the new drawing. So we already found out that according to rule 10, PTQ is one side line. If PTQ is one side line, it means that PQ in total must be equal to PT plus TQ. So PQ equals to PT. PT is the radius of this semicircle, that is 2, plus TQ. TQ is the radius of this small semicircle, that is 1. So in total we found out that PQ equals to 2 plus 1, that is 3. So PQ equals to 3 units in its length. Qn equals to 1 unit in its length, and PM equals to 2 units in its length. Those two angles are both right angles according to rule 1. So actually, this is quadrilateral PQMN that I copied from the original drawing. In the next step, we will do a construction, that is to say from point Q, we will go perpendicular on PM. Again, from point Q, we will go perpendicular on PM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and PM. This point is point N. PM equals to 2, this is the radius of the semicircle, it equals to 2. By doing this construction, you can reveal the small quadrilateral LQ and M. Inside the small quadrilateral LQ and M, we have 1, 2, 3 right angles. Therefore, this fourth angle must be equal to 90 degrees in size, according to the rule that said that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral LQ and M, we have 4 right angles, and therefore it is a right angle. But we also know that the opposite sides of right angle are equal to each other. So in right angle NQ and M, side QN must be equal to the opposite side LN, but QN is 1, therefore the opposite side LN must be also equal to 1 unit in its length. What is the length of the missing 9/7 PL? PL equals to PM minus LM. So write it down. The missing side PL is equal to PM minus LM. So PL, the missing side PL equals to PM, that is 2, minus LM, that is 1. So in total, PL equals to 2 minus 1, that is 1. PL equals to 1 units in its length. In the next step, we'll implement the Pythagoras theorem on this right triangle PLQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle PLQ, PQ square, the square of the hypotenuse, equals to PL square plus LQ square. So the norm. Here by PT, evaluation for Pythagoras theorem. So a PQ square, that is the square of the hypotenuse, equals to PL square plus LQ square. PL is 3, therefore PL square is 3 squared, that is 9. And it equals to PL square, PL is 1, therefore PL square is 1 squared, that is 1, plus LQ square. LQ is the missing side, so it is LQ square. So in total, we found out that 9 equals to 1 plus LQ square. Here we subtract 1 from the equation, and finding that LQ square equals to 9 plus 1 is 8. LQ square equals to 8. Here we take out all of the equation, and finding that LQ equals to the square root of 8 units in its length. It's 8 by 4 times 2, so it equals to the square root of 4 times 2. The square root of 4 is 2, so inside the root we left only with 2. So in total we found out that LQ equals to 2 times square root of 2 units in its length. But we also know that the opposite sides of a rectangle are equal to each other. So in the small rectangle LQ and M, side LQ must be equal to the opposite side MN, but LQ equals to 2 times square root of 2, therefore the opposite side MN must be also equal to 2 times square root of 2 units in its length. So MN equals to 2 times square root of 2 units in its length. We define the length of line segment MO as A. So what is the length of line segment ON? ON equals to MN plus MO. So the norm ON equals to MN minus MO. So in total ON equals to MN. MN is 2 times square root of 2 minus MO. MO is A. So in total ON equals to 2 times square root of 2 minus 3 units in its length. In the next step, we'll join points O and Q together by straight line. Point O is the center of the biggest semicircle. Point Q is the midpoint of chord EF. Again, point Q is the midpoint of chord EF. And of course it is the center of this small semicircle. So EQ is the radius of this small semicircle, equals to 1. Likewise, QF is also the radius of this small semicircle, equals to 1. So OQ, line segment OQ that is drawn from the center of the biggest semicircle, that is to say from this point O, line segment OQ bisects chord EF. Why? Because at point Q, chord EF has been bisected into two halves. The first half equals to EQ, that is 1. The second half QF also equals to 1 unit in itself. So OQ bisects chord EF. Again, OQ bisects chord EF. And therefore, you can implement here rule 30. Please click on rule 30. According to rule 30, a line segment that is drawn from the center of a circle and bisect the chord will be also perpendicular to that chord. In the drawing, we have a circle. This is point O, that is the center of this circle. This is chord AB. Line segment OM bisect chord AB. Again, line segment OM bisects chord AB according to our construction. That is to say, AM equals to MB equals to AB over 2. And because of the fact that line segment OM bisects chord AB, line segment OM will be also perpendicular to chord AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 30. So whenever you have a line segment that is drawn from the center of the circle and bisects a chord, then that line segment also will be also perpendicular to that chord. Here line segment OM bisects chord AB, and therefore line segment OM is perpendicular to AB. So we can implement rule 30 in our drawing. In our drawing, from the center of the biggest semicircle, that is to say from point O, we have line segment OQ, it bisects chord EF. According to rule 30, line segment OQ will be also perpendicular to chord EF. If OQ is perpendicular to EF, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees, according to rule 30. So in the next step, we join points E and Q together by straight line. Point O is the center of the biggest semicircle. Point E is the point of the biggest semicircle itself. Therefore, OE is the radius of this big semicircle. We define the radius of the big semicircle as R. We define the radius of the biggest semicircle as X. So O equals to X according to our definition. So in the next step, we'll implement the Pythagoras theorem on this green right triangle EQO. And again, we'll implement the Pythagoras theorem on this green right triangle EQO. Here by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, this right line EQO EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. And again, in this right-hand line EQO, according to the Pythagoras theorem, EO squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. The hypotenuse EO equals to x, therefore EO squared is x squared. And it is equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared, that is 1, plus QO squared. QO is one side of this green right triangle EQO, but QO is also the hypotenuse of this right triangle QNO. And again, QO is also the hypotenuse of this right triangle QNO. QO is the hypotenuse of the pink right triangle QNO. So if we implement the Pythagoras theorem on the pink right triangle QNO, we get that QO squared, that is the square of the hypotenuse, equals to QN squared plus NO squared. And again, QO squared equals to QN squared plus NO squared. QO squared equals to QN squared plus NO squared. EQ equals 1, therefore Q squared is 1 squared, that is 1. EO equals to x, and therefore EO squared equals to x squared, that is EO squared equals to x squared. So we found out that x squared equals to 1 plus NQ squared plus NO squared. So x squared according to equation 1, x squared equals to 1 plus Qn squared. Qn is also 1, therefore Qn squared is 1 squared, that is 1 plus NO squared. NO equals to 2 times square root of 2 minus 8, therefore NO squared is 2 times square root of 2 minus 8 squared. So according to equation 1, from order 3, that x squared equals to 1 plus 1 plus 2 times square root of 2 minus 8 squared. So x squared equals to 1 plus 1 is 2 plus 2 times square root of 2 minus 8 squared equals to 2 times square root of 2 squared, that is 8 plus 8 squared minus 2 times square root of 2 times a. So according to equation 1, we found out that x squared equals to 2 plus 8 is 10 plus a squared, and we have here minus 2 times 2 is minus 4, so this expression equals to minus 4 times square root of 2 times a. So in total, according to equation 1, we shall find out that x squared equals to 10 plus a squared minus 4 times square root of 2 times a. In the next step, we repeat on the same process that we did here on this side of the big semicircle, on this side of this big semicircle. That is to say, we join points O and P together by a straight line. Point P is the center of this semicircle. CP is the radius, so this is 2. PD is also the radius of this semicircle, that is 2. So CD is the diameter of this semicircle, and P is the center of this semicircle. So point P is the midpoint of CD. Again, point P is the midpoint of CD. So it's point P, CD has been bisected into 2 halves. The first half is PD, that is 2. The second half is PC, that is also 2. So you can implement here rule 30 because we have the radius OP, line segment OP bisects chord CD. Again, line segment OP bisects chord CD. Divides chord CD into 2 halves. The first half is DP, that is 2. The second half is PC, that is also 2. And therefore, according to rule 30, whenever you have a line segment that is drawn from the center of the circle and bisects a chord, then that line segment will be also perpendicular to that chord. That is to say, line segment OP must be also perpendicular to chord DC. If OP is perpendicular to DC, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 30. In the next step, we'll join points O and C together by a straight line. Point O is the center of the biggest semicircle, point C is the point of the biggest semicircle itself, therefore OC is the radius of this biggest semicircle, that is x. OC equals to x. The next step, we implement the Pythagoras theorem on this green triangle CPO. Here by PT is the version of Pythagoras theorem. So in this green right triangle CPO, CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. But again, according to the Pythagoras theorem, this right triangle CPO CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. CO is x, therefore CO squared is x squared. And is equals to Cp squared. Cp is 2, therefore Cp squared is 2 squared, that is 4, plus Po squared. What is the value of Po? Po is one side of the green right triangle CPO, but Po is also the hypotenuse of the right triangle PMO. Again, PO is also the hypotenuse of this right pink triangle PMO. So we represent the bottom term on this right pink triangle PMO and get that according to the bottom term on this right triangle PMO, PO square equals to PM square plus MO square. Repeat again. CO equals to x, therefore CO square is x square, and it equals to Cp square. Cp is 2, therefore Cp square is 2 square, that is 4, plus Po square. Po is the hypotenuse of this right triangle PMO, therefore, according to the bottom theorem, Po square equals to PM square plus MO square. Again, Po square equals to PM square plus MO square. So total according to equation 2, x square equals to 4 plus PM square plus MO square. PM is 2, therefore PM square is 2 square, that is 4, plus MO square. MO is 8, therefore MO square is 8 square. So in total, according to equation 2, I can find out that x square equals to 4 plus 4 plus 8 square. According to equation 2, x square equals to 4 plus 4 is 8 plus 8 square. This is according to equation 2. Again, according to equation 2, I should find out that x square equals to 8 plus 8 square, while according to equation 1, we already found out that x square equals to 10 plus 8 square plus 4 times square root of 2 times 8. So we have these are the questions for x square. Therefore, we get the question 3. It states that x square according to equation 1 must be equal to x square according to equation 2. X square according to equation 1 equals to 10 plus a squared minus 4 times square root of 2 times a, and it must be equal to x squared according to equation 2. X squared according to equation 2 equals to 8 plus a squared. So in total according to equation 3, we found out that 10 plus a squared minus 4 times square root of 2 times a equals to 8 plus a squared. We have a squared on both sides of the equation, so a squared will get cancelled. Here we subtract 8 from this equation 3, and we get that according to equation 3, 10 minus 8 is 2. So here we have 2 minus 4 times square root of 2 times a equals to 8 minus 8 is 0, equals to 0. So here we add 4 times square root of 2 times a to this equation. Again, according to equation 3, 2 equals to 4 times square root of 2 times A. Here we divide this equation 3 by 2. Finding again that according to equation 3, 2 over 2 is 1 equals to 4 over 2 is 2, so in total this expression equals to 2 times root of 2 times A. So 1 equals to 2 times root of 2 times A. Here we divide this equation 3 by 2 times root of 2, and finding again that according to equation 3, A equals to 1 over 2 times root of 2 units in its length. And again, A equals to 1 over 2 times root of 2 units in its length. According to equation 2, we already found out that x squared equals to 8 plus A squared. So x squared equals to 8 plus A squared. A is 1 over 2 times root of 2, and therefore A squared must be equal to 1 over 2 times root of 2 squared, that is 8. So in total we should find out that x squared equals to 8 plus 1/8. So x squared equals to 1/8 plus 8. So here we'll multiply 8 by 8 and then we divide it by 8 in order to come out with this number. We get that 8 times 8 is 64 divided by 8. 64 plus 1 is 65 over 8. So in total we found out that x squared equals to 65 over 8 units, 65 over 8. Our task is to find out the size of this shaded area, shaded region. From the drawing, it's very easy to see that the size of this shaded region must be equal to the area of the big semicircle minus the area of this small semicircle, the left semicircle minus the area of this right semicircle. Again, the size of this area in total equals to the area of the biggest semicircle minus the area of this semicircle minus the area of the other this semicircle. So writing down. So the size of this shaded area in total it must be equal to the area of the biggest semicircle minus the area of the left semicircle minus the area of the right semicircle. And again, the size of the shaded area in total must be equal to the area of the biggest semicircle minus the area of this left semicircle minus the area of this right semicircle. What is the area of the biggest semicircle? The radius of this biggest semicircle is x, therefore the area must be equal to pi x squared over 2. The area of the biggest semicircle is equal to pi x squared over 2 minus the area of this left semicircle. The radius of this left semicircle is 2, therefore the area must be equal to pi 2 squared over 2. And the left semicircle equals to pi 2 squared over 2. Also, the area of the right semicircle, the radius of this right semicircle is 1, and therefore the area must be equal to pi 1 square over 2. So here we take pi over 2 as a common factor from those first expressions. So inside the brackets we left only with x squared, minus 2 squared that is minus 4, minus 1 squared that is minus 1. So if we found out that the size of the shaded area equals to pi over 2 times x squared minus 4 minus 1. So it is pi over 2, x squared is 65 over 8, minus 1, minus 4 is minus 5. So total, the size of the shaded area equals to pi over 2 times 65 over 8 minus 5. So here we multiply minus 5 by 8 and then divide it by 8 in order to account for the factor with this number. We get that the size of the shaded area in total must be equal to pi over 2. We have 65 over 8. Minus 5 times 8 is minus 40 divided by 8. So total, the size of the shaded area is equal to pi over 2. And we have 65 minus 40 is 25 over 8. So the size of the shaded area equals to 25 pi over 2 times 8 is 16. So in total, if you found out that the size of this shaded area equals to the 25 pi over 16 square units in size, or in terms of numbers, is equal to 4.908 square units in size. Again, if you found out that the size of this shaded area, in total it is equal to either 25 pi over 16 square units in size, or in terms of numbers it is equal to 4.908 square units in size. So, finished to answer the first question. In the next step, I present you the second question and resolve the second question of this lecture. In the second question, our task is to find out the size of this shaded area. The shaded area is located inside this small semicircle, so our task is to find out the size of this, the area of this small semicircle. Okay. So in the drawing, we have two semicircles that intersect with each other. This is the big semicircle. AB is the diameter of this big semicircle. AB in total equals to AM, that is 3, plus MN, that is also 3, plus NB, that is 2. So total AB equals to 3 plus 3 plus 2, that is 8. The diameter AB of the big semicircle equals to 3 plus 3 plus 2, that is 8. AB equals to 8. So we define the radius of this big semicircle as R. So the radius R must be equal to the diameter AB over 2. So it is 8 over 2, that is 4. So if you found out that the radius R of this big semicircle equals to 4 units in its length. We find the center of this big semicircle, this point is point O. We find the center of this small semicircle, this point is point S. what is the length of this line segment? MO. MO equals to AO minus AM. MO equals to AO minus AM. So in total, MO equals to AO, that is 4, it is the radius of the big semicircle, that is 4. Minus AM is 3, according to what is given in the question. So in total, MO equals to 4 minus 3, that is 1. MO equals to 1 unit in its length. This is the answer in MO equals to 1 unit in its length. In the next step, we will do a construction. That is to say, from point S, that is the center of this small semicircle, we will do perpendicular on chord MN. Again, from point S, we will do perpendicular on chord MN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point S and called MN. This point is point T. We define the length of line segment ST, SH. So from point S, that is the center of this small semicircle, we do perpendicular ST on chord MN. Again, from point S, that is the center of this small semicircle, we draw perpendicular ST on chord MN. And whenever you draw a perpendicular from the center of the circle towards any chord, it will bisect the chord. Again, according to rule 15, whenever you draw a line segment that is drawn from the center of the circle towards any chord, it will bisect the chord. So, from the center of this small semicircle, that is also from point S, we do perpendicular on chord MN. And therefore, according to rule 15, it will bisect chord MN. The first half will be equal to MT. It is of course equal to the second half Tn. And each half must be equal to Mn over 2. So pinch quickly. Yeah. Perpendicular ST bisect chord Mn. So the first half is MT, the second half of Mn is Tn, and each half of course equals to Mn over 2 because Mn has been bisected. So pinch quickly on rule 15, according to rule 15, the perpendicular from the center of the circle towards any chord bisect the chord. In the drawing circle, Mn is a chord inside this circle. This is perpendicular ST, that is drawn from point S, that is the center of the circle. According to this rule, rule 15, perpendicular ST bisect chord Mn. If ST is if perpendicular ST bisects chord Mn, it means that MT equals to Tn equals to Mn over 2. Solution 4. Perpendicular ST bisects chord Mn. So the first half is MT, of course equals to the second half Tn. Each half must be equal to Mn over 2. So that is known. According to rule 15, perpendicular ST bisect chord Mn. The first half is MT. It is of course equal to the second half of Mn, that is Tn. and each half must be equal to mn over 2 because mn is being bisected. And again, the first half mt equals to the second half tn, and each half must be equal to mn over 2. Mn is 3, so mn over 2 is 3 over 2, this is 1.5. So mt equals to tn equals to 1.5 minutes in its length. Mt equals to 1.5. This is the line, so at the end is equal to 1.5 and mt is also equal to 1.5 minutes in its length. What is the length of this missing line 7 OT? From the drawing, it is very easy to see that OT in total must be equal to MT minus MO. See again, the short line segment OT equals to MT minus MO. So OT equals to MT is 1.5 minus MO, that is 1. So in total, OT equals to 1.5 minus 1, that is 1 half. So OT equals to 1 half units in its length. This is the short line segment OT, it equals to 1 half units in its length. In the next step, we will join points O and S together by a straight line. Point S is the center of this small semicircle. If we define the radius of this small semicircle as x, and SQ is the radius of this small semicircle, this equals to x. Likewise, SP is also the radius of this small semicircle, is equals to x. So from point O, that is the center of this big semicircle, we have line segment OS that bisects chord PQ. Again, from point O, that is the center of this big semicircle, we have line segment OS that bisects chord PQ. PQ in total equals to 2x, it is the diameter of this small semicircle, so each half equals to x. The first half PS equals to 2x, and the second half SQ also equals to x. It is the area of the small semicircle. So from the center of this big semicircle, we have line segment OS that bisects chord PQ. And now, from the center of the circle, we have, or a semicircle or circle, we have a line segment that bisects a chord. The line segment must be also perpendicular to that chord according to rule 30. So if it will be on rule 30, according to rule 30, a line segment that is drawn from the center of a circle and bisects a chord will be also perpendicular to that chord. And the drawing in a circle, point O is the center of this circle. Line segment OM bisects chord AB according to our construction. Again, line segment OM bisects chord AB according to our construction. That is to say, AM equals to MB equals to AB over 2. And because of the fact that OM bisects chord AB, OM must be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 30. We can actually implement Rule 30 in our drawing, right? Because in our drawing, from the center of this big semicircle, this is to say from this point O, we have line segment OS that bisects chord PQ. And therefore, according to Rule 30, line segment OS will be also perpendicular to PQ. If OS is perpendicular to PQ, it means that this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees. So in the next step, I'll copy the small right triangle SOT in a new page, and we will implement the Pythagoras theorem on this small right triangle OST. Here by PT, the version for the Pythagoras theorem. We define line segment OS as Y. So here by PT is the version for Pythagoras theorem. Actually, this is the right triangle OST, this is the point from the original line. In this right triangle OST, SO squared, this is the square of the hypotenuse, equals to ST squared plus TO squared. So as you know, so SO squared, that is the square of the hypotenuse, equals to ST squared plus OT squared. SO is Y, therefore SO squared is Y squared, and it equals to ST squared. ST is 8, therefore ST squared is 8 squared, plus OT squared. OT is 1/2, therefore OT squared is 1/2 squared, that is 1/4. So in total, according to equation 1, we have found out that Y squared equals to 8 squared plus 1/4. In the next step, we join points S and N together by side 9. Point S is the center of this small semicircle, point N is the point of the small semicircle itself, therefore Sn is the radius of this small semicircle, equals to X. So in the next step, we implement the Pythagoras theorem on this right triangle STN. So I copy the right triangle STN in the equation, we will implement on it the Pythagoras theorem. Tn equals to 1.5 units in its length. It's actually 3 over 2 units. So actually, this is the right angle STN that the corresponding original domain. In this right angle STN, Sn squared, that is the square of the hypotenuse, equals to St squared plus Tn squared. Sn equals to x, so therefore Sn squared equals to x squared. This equals to St squared. St is x, therefore St squared is h squared plus Tn squared. Tn is 3 over 2, therefore Tn squared is 3 over 2 squared, that is 9 quarters. So total, according to equation 2, if you found out that x squared equals to h squared plus 9 quarters. And according to equation 1, we already found out that y squared equals to h squared plus 1 quarter. Okay, again, according to equation 2, x squared equals to h squared plus 9 quarters. While according to equation 1, y squared equals to h squared plus 1 quarter. So we subtract those two expressions and form those two equations from each other. Equation 2 minus equation 1. This way we get equation 3 that says that x squared minus y squared equals to h squared plus 9 quarters minus h squared plus 1 quarter. So it is equation 2 minus equation 1. So according to equation 3, we found out that x squared minus y squared equals to h squared plus 9 quarters. Here we open the brackets and get that minus h squared minus 1 quarter. So we have here h squared minus h squared is 0, 9 quarters minus 1 quarter is 8 quarters, 8 quarters is 2. So in total, according to equation 3, if we found out that x squared minus y squared equals to 2. In the next step, we will join points O and P together by straight line. Point O is the center of this big semicircle, point P is the point of the big semicircle itself. Therefore, OP is the radius of the big semicircle, and it equals to 4, according to what we already found out. So OP is the radius of the semicircle, the big semicircle is equals to 4. So in the next step, I'll copy the right triangle POS in a new page and we'll implement on it the Pythagoras theorem. I say that SO equals to Y according to our definition. So actually, this is the right triangle PSO that comes from the original drawing. In this right triangle PSO according to the Pythagoras theorem, PO square, that is the square of the hypotenuse, equals to PS square plus SO square. PO equals to 4, therefore PO square is 4 square, that is 16. And it equals to PS square. PS is x, therefore PS square is x square, plus SO square. SO is y, therefore SO square is y square. So in total, according to equation 4, we found out that 16 equals to x square plus y square, or according to equation 4, x square plus y square equals to 16. This is according to equation 4, or according to equation 3, we already found out that x square plus y square equals to 2. And again, we have two equations. According to equation 2, x square plus y square equals to 16, and according to equation 3, x square plus y square equals to 2. Here we let equation 4 to equation 3, and then those two equations with each other. And get that this will be equation 5, x square plus x square is 2x square, and y square minus y square is 0, and it is equals to 16 plus 2, that is 18. So in total, according to equation 5, we actually found out that 2x squared equals to 18. Here we divide this equation 5 by 2, and find again that according to equation 5, x equals to 18 over 2 is 9. Again, we divided the equation 5 by 2, so 2x squared over 2 is x squared equals to 18 over 2, that is 9. So in total, according to equation 5, we actually found out that x squared equals to 9. Our task is to find out the size of this shaded area. The shaded area is the area of this small semicircle. So we have to find out the area of this small semicircle. The radius of this small semicircle is x, and therefore the area of this small semicircle must be equal to pi x squared over 2. So it's pi over 2 times x squared. X squared is 9, so it's x squared by 9. Get that the size of the shaded area equals to 9 pi over 2. 9 over 2 is 4.5 pi. So in total, if you found out that the size of this shaded area, that's actually the area of this small semicircle, it is equal to either 4.5 pi square inches in size, so in terms of numbers, it is equal to 14.137 square inches in size. And again, if you found out that the size of this shaded area equals to either 4.5 pi square inches in size, or in terms of numbers, it is equals to 14.137 square inches in size. So finish to answer on the second question. The next step, I will summarize the lecture. I will start with the first question, of course. So repeat on the solution of the first question. In the first question, our task was to find out the size of this shaded region. So in the drawing, we have 3 semicircles. This is the biggest semicircle. Inside this biggest semicircle, we have those 2 smaller semicircles. The radius of this semicircle is 2. The radius of this semicircle is 1. Again, our task is to find out the size of this shaded area. So first of all, we define the center of this semicircle. This point is point P. We define the center of this semicircle. This point is point Q. We defined the point of tendency of tangent AB with this semicircle. This point is point M. And finally, we defined the point of tendency of tangent AB with this semicircle. This point is point M. So here we can implement rule 1, because we have the radius PM that is equals to 2. The radius PM is drawn to point M, that is the point of tendency of tangent AB with this semicircle. And whenever your radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MP. If AB is perpendicular to MP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we have the radius Qn is equals to 1. Radius Qn equals to 1. Radius Qn is drawn to point N. That is the point of tendency of tangent AB with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NQ. If AB is perpendicular to NQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the sum of rule 1. So here we have an external between those 2 small semicircles at this point T. That is to say, they touch each other externally at this point T. And whenever you have an external between 2 circles or semicircles, you can implement rule 10. You can take rule 10. According to rule 10, if 2 circles touch each other externally, then the straight line that connects the circles together passes through their touching points. The line, we have those 2 circles that touch each other externally, this point P. The center of this circle is at point O. The center of this circle is at point M. The straight line that connects the circles together is of course the straight line OM. So this straight line OM must pass through point P, that is the touching point. Or OPM is one straight line. Again, according to this rule, OPM is one straight line. So we can implement rule 10 in our drawing. Those 2 circles are external lines between them at point T. The center of this semicircle is here at point P. The center of this small semicircle is here at point Q. The straight line that connects the circles together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through point T, that is their touching point. Again, the straight line PQ must pass through point T, that is their touching point, or PTQ is one straight line. If PTQ is one straight line, it means that PQ in total must be equal to PT plus TQ. So PQ in total must be equal to PT. PT is the radius of this semicircle, that is 2, plus TQ, that is 1. Is the radius of this small semicircle, that is 1. So in total, PQ equals to 2 plus 1, that is 3. PQ equals to 3 units in its length. So in the next step, I copied this quadrangle PQ and M in a new page, and we did a construction on the new drawing. This is quadrangle PQ and M that I copied from the original drawing. This quadrangle PQ and M from point Q, we do perpendicular on PM. Again, from point Q, we do perpendicular on PM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and side PM. This point is point F. By doing this construction, we get another quadrangle LQ and M. Inside quadrangle LQ and M, we have 1, 2, 3 angles, and therefore this surface angle must be equal to 90 degrees in its size according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this surface angle must be equal to 90 degrees in its size. So in quadrangle LQ and M we have 4 angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So the rectangle LQ and M, side QN must be equal to the opposite side LM, but QN is 1, therefore the opposite side LM must be also equal to 1 inch in its length. What is the length of this missing line segment? PL. What is the length of this missing line segment? Line segment PL. PL equals to PM minus LM. So PL equals to PM, that is 2, minus LM, that is 1. So PL equals to 2 minus 1, that is 1. PL equals to 1 unit in its length. In the next step, we implemented the Pythagoras theorem on this right triangle PLQ. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendicular. So in this right triangle PLQ, PQ squared, that is the square of the hypotenuse, equals to PL squared plus LQ squared. PQ is 3, therefore PQ squared is 3 squared, that is 9 plus, so 9 equals to PL squared. PL is 1, therefore PL squared is 1 squared, that is 1. Plus LQ squared. LQ is the missing side, so it is. So in total, we should know that 9 equals to 1 plus LQ squared. Here, so subtract the 1 from this equation, and find out that 9 minus 1 is 8, equals to LQ squared. Here we took out of this equation, and find out that LQ equals to the square root of 8. We substitute 8 by 4 times 2, so we found out that LQ equals to the square root of 4 times 2. The square root of 4 is 2, so inside the root we left only with 2. So in total, we found out that LQ equals to 2 times square root of 2 units in its length. The opposite sides of rectangle LQ and M are equal to each other. So side LQ equals to the opposite side MN, but LQ is 2 times square root of 2, therefore the opposite side MN must also equal to 2 times square root of 2 units in its length. This is line segment MN, that equals to 2 times square root of 2 units in its length. We define the length of line segment MO. This line segment MO is 8, therefore ON must be equal to MN minus MO. And ON equals to MN minus MO. So ON in total equals to MN, that is 2 times square root of 2, minus MO, that is 8. So in total, ON equals to 2 times square root of 2, minus 1 units in its length. In the next step, we join point O and Q together by straight line. Point O is the center of this biggest semicircle. Point Q is the midpoint of chord EF. So this is the center of this small semicircle. At point Q, chord EF has been bisected into 2 halves. The first half EQ is 1, the second half QF is also 1. And whenever you have from the center of the circle or the semicircle a line segment that bisects a chord, that line segment must be also perpendicular to that chord. Line segment OQ bisects chord EF, and therefore line segment OQ must be also perpendicular to EF. If OQ is perpendicular to EF, it means that this angle was 90 degrees, and this angle also was 90 degrees, according to Rule 30. So I put it on Rule 30. According to Rule 30, a line segment that is drawn from the center of the circle and bisects the chord will be also perpendicular to that chord. In the drawing, we have a circle, point O is the center of this circle, we have a chord AB. Line segment OM bisects chord AB. That is to say, AM equals to MB equals to AB over 2. And because of the fact that OM bisects chord AB, OM will be also perpendicular to AB. If OM is perpendicular to AB, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule, Rule 30. So as you said before, we can implement Rule 30 in our drawing. One because in our drawing, we have line segment OQ that bisects chord EF, and therefore line segment OQ will be also perpendicular to EF. If OQ is perpendicular to EF, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 30. So in the next step, we implemented the Pythagoras theorem. We join points O and D together, O and D together by straight line. Point O is the center of the biggest semicircle, point A is the point of the biggest semicircle itself, therefore O is the radius of the biggest semicircle, that is equal to X according to our definition. So in the next step, we implemented the Pythagoras theorem. The Pythagoras theorem on this line OEQ. On this line OEQ, O E squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. O E squared, that is the square of the hypotenuse, equals to EQ squared plus QO squared. OE is X, therefore O squared is X squared, and it equals to EQ squared. EQ is 1, therefore EQ squared is 1 squared. That is 1. So EQ squared equals to X squared, EO squared equals to X squared, EQ squared equals to 1. And we have also plus QO squared, because EO squared equals to EQ squared plus QO squared. So QO is the opposite of this pink triangle, and therefore QO square equals to QN square plus NO square. QO square equals to QN square plus NO square. So in total, x square equals to 1 plus QN square plus NO square. So x square equals to 1 plus QN square. QN is 1, therefore QN square is 1 squared, that is 1. Plus NO square. NO is 2 times square root of 2 minus 8, therefore NO square is 2 times square root of 2 minus 8 square. So in total, according to equation 1, if we found out that x square equals to 1 plus 1 plus 2 times square root of 2 minus 8 square. So x square equals to 1 plus 1, that is 2. We open the brackets of this expression. If we found out that 2 times square root of 2 times a equals to 2 times square root of 2 squared, that is 8, plus a square minus 2 times square root of 2 times 2 times a. So x square equals to 8, 2 plus 8 is 10, and we have plus a square, and minus 2 times 2 is minus 4, so in total this expression equals to minus 4 times square root of 2 times a. So in total, according to equation 1, we found out that x square equals to 10 plus a square minus 4 times square root of 2 times a. In the next step, we repeated on the same process that we did in this side of this big semicircle on this side. That is to say, we join points O and P together by a straight line. Point O is the center of this biggest semicircle. Point P is the midpoint of CD. It is the center of this semicircle. So we have chord O, line segment OP by self chord CD. CD is the diameter of the semicircle at point P. Point P is the center of the semicircle. So CD is bisected into two halves at point P. So OP bisects chord CD, and therefore OP must be also perpendicular to chord CD according to Rule 30. Again, because of the fact that OP bisects chord CD, OP must be also perpendicular to CD. If OP is perpendicular to CD, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 30. In the next step, we join points O and C together by a straight line. OC is the radius of the biggest semicircle, that is x. The next step, we implemented the Pythagoras theorem on this right triangle CPO. This right triangle CPO, CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. Okay, again, according to the Pythagoras theorem, this right triangle CPO, CO squared, that is the square of the hypotenuse, equals to CP squared plus PO squared. CO is x, therefore CO squared is x squared, and it equals to CP squared. CP is 2, therefore CP squared is 2 squared, that is 4. We have plus PO square. PO is the opposite of this pink triangle PMO, therefore PO square must be equal to PM square plus MO square. Again, PO square equals to PM square plus MO square. So in total, x square equals to 4 plus PM square plus MO square. So x square equals to 4, and we have plus PM square. PM is 2, therefore PM square is 2 squared, that is 4. Plus MO square. MO is 8, therefore MO square is a square. So if we know that x square equals to 4 plus 4 plus a square. 4 plus 4 is 8, so in total, according to equation 2, x square equals to 8 plus a square. This is according to equation 2, and according to equation 1, we only found out that x square equals to 10 plus a square plus 4 times square root of 2 times a. So we have two different equations for x square. Therefore, we get the equation 3 that says that x square according to equation 1 must be equal to x square according to equation 2. X square according to equation 1 equals to 10 plus a square minus 4 times square root of 2 times a. It must be equal to x square according to equation 2. X square according to equation 2 equals to 8 plus a square. So in total, we found out that 10 plus a square minus 4 times square root of 2 times a equals to 8 plus a square. We have a square on both sides of this equation, so a square will get cancelled. Here we subtract 8 from this equation, and we found out that 10 minus 8 is 2, minus 4 times square root of 2 times a equals to 8 minus 8 is 0. So in total, 2 minus 4 times square root of 2 times a equals to 0. Here we add 4 times square root of 2 times a to the equation, and we found out that 2 equals to 4 times square root of 2 times a. Here we divided this equation 3 by 2, and we found out that 2 over 2 is 1, and it equals to 4 over 2, that is 2 So in total, this expression equals to 2 times root of 2 times 8. So 1 equals to 2 times root of 2 times 8. Here we divided the equation 3 by 2 times root of 2, and finally found out that a equals to 1 over 2 times root of 2. According to equation 2, we found out that x squared equals to 8 plus 8 squared. So x squared equals to 8 plus 8 squared. A is 1 over 2 times root of 2, and therefore a squared must be equal to 1 over 2 times root of 2 squared, that is 8. So in total x squared equals to 8 plus 1 8. So x squared equals to 1 8. Here we multiply 8 by 8 and then we divide it by 8 in order to account factor with this number. So 8 times x is 64 divided by 8. So 64 plus 1 is 65 over 8. So in total, if you found out that x squared equals to 65 over 8. Our test is to find out the size of this shaded area. The size of this shaded area must be equal to the area of the biggest semicircle minus the area of the small left circle minus the area of the right circle. Again, the size of the shaded area in total must be equal to the area of the biggest semicircle minus the area of the left semicircle minus the area of the right semicircle. The radius of the biggest semicircle is x, therefore the area must be equal to pi x squared over 2. The radius of the left semicircle is 1, therefore the area of the left semicircle must be equal to pi 2 squared over 2. The radius of the right semicircle is 1, therefore the area must be equal to pi 1 squared over 2. So in total, the size of the shaded area equals to pi x squared over 2 minus pi 2 squared over 2 minus pi 1 squared over 2. Here we took pi over 2 as a common factor from those two expressions, so inside the brackets we left with x squared minus 4 minus 1. X squared is 65 over 8, minus 4 minus 1 is minus 5. So in total, the size of the shaded area equals to pi over 2 times 65 over 8 minus 5. Here we multiplied minus 5 by 8 and then we divided by 8 in order to account factor with this number. If you found out that the size of the shaded area equals to pi over 2, and we have minus 5 times 8 is minus 40 divided by 8. So in total, the size of the shaded area equals to pi over 2, and 65 minus 40 is 25 divided by 2 times 8. So in the numerator we have 25 pi over 2 times 8, that is 16. So in total, I should found out that the size of this shaded area is equal to either 25 pi over 16 square units in size, or in terms of numbers, the size of this shaded area equals to 4.908 square units in size. So finish to repeat on the first question. In the next step, I repeat on the solution of the second question. So our task in the second question is to find out the size of this shaded area. The shaded area is this small semicircle. So we have to find out the area of this small semicircle. So in the drawing you have two semicircles that intersect with each other. And this is the big semicircle. AB is the diameter of this big semicircle. AB in total equals to AM that is 3, plus MN that is also 3, plus NB that is 2. So in total AB equals to 3 plus 3 plus 2, that is 8. The diameter AB of the big semicircle equals to 3 plus 3 plus 2, that is 8. Therefore, the radius of the big semicircle must be equal to the diameter AB over 2. That is to say, since 8 over 2, that is 4. So the radius of this big semicircle, the radius equals to 4. AO is the radius of the big semicircle. This big semicircle is equals to 4. AM equals to 3. Therefore, MO must be equal to AO minus AM. Again, M1 equals to AO minus AM. AO is 4, it is the radius of the big semicircle, minus AM. AM is 3, so in total M1 equals to 4 minus 3, this is 1. Minus M1 equals to 1 unit in its length. The next step, we did the construction, that is to say, from point C, we do perpendicular on chord MN. Again, from point S, that is the center of this small semicircle, we do perpendicular ST on chord MN. And whenever you draw a perpendicular from the center of the circle or semicircle towards any chord, it will bisect the chord according to Rule 15. Perpendicular ST bisect chord MN according to Rule 15. So if perpendicular ST bisects chord MN, it means that the first half MT must be equal to the second half TN, and each half must be equal to MN over 2 because MN has been bisected. According to Rule 15, perpendicular ST bisects chord MN. The first half is MT, is equal to the second half TN. Each half must be equal to MN over 2. MN is 3, so it is MN over 2 is 3 over 2, that is 1.5. So the first half MT equals to 1.5, and the second half TN, must be also equal to 1.5 units in its length. We define the length of line segment ST as H, and then we join points S and O together by straight line. So from the center of this big semicircle, that is to say from this point O, we draw line segment OS. Line segment OS bisects the diameter PQ. The diameter PQ in totality is 2x, so each half equals to x. Px equals to x, and the second half SQ also equals to x. So because of the fact that from the center of this big semicircle, that is to say from point O, we have a line segment OS that bisects chord PQ. Line segment OS must be also perpendicular to chord PQ according to Rule 30. Again, because of the fact that line segment OS bisects chord PQ, line segment OS must be also perpendicular to PQ. If OS is perpendicular to PQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to Rule 30. What is left from this line segment OT? OT equals to MT minus MO. OT equals to MT minus MO. MT is 1.5, MO is 1. So in total, OT equals to 1.5 minus 1, that is 1 half. So OT equals to 1 half units in its length. In the next step, I copied the right triangle SOT in an equation we implemented on it, the Pythagoras theorem. This is the right triangle SOT that I copied from the original drawing. This right triangle SOT, SO squared, that is the square after we define the length of side SO is y and the length of side ST is h. We just write down found out that OT equals to 1 half units in its length. In this right triangle SOT, SO squared, that is the square of the opposite, equals to ST squared plus TO squared. SO is y, therefore SO squared is y squared, and it is equals to ST squared. ST is h, therefore ST squared is h squared, plus TO squared. TO is 1 half, therefore TO squared is 1 half squared, that is 1 quarter. So total according to equation 1, y squared equals to h squared plus 1 quarter. In the next step, we join points S and N together by straight line. Point S is the center of this small semicircle, point N is the point of the small semicircle itself, therefore Sn is the radius of this small semicircle, is equals to x. In the next step, I copied the right triangle STN in a new page and implemented the Pythagoras theorem on this right triangle STN. This is the right triangle STN that I copied from the original drawing. Tn equals to 1.5. st equals to h, and Sn is the radius of the small semicircle that is equals to x. This triangle is Tn, Sn squared is the square of the hypotenuse equals to st squared plus Tn squared. Sn is x, therefore Sn squared is x squared, and it is equals to st squared. St is h, therefore st squared is h squared plus Tn squared. Tn is Tn is 3 quarters. Tn is 3 over 2. Therefore, Tn squared is 3 over 2 squared, that is 9 quarters. So in total, according to equation 2, we should find out that x squared equals to h squared plus 9 quarters. And again, according to equation 2, we just let them find out that x squared equals to h squared plus 9 quarters, while according to equation 1, we already found out that y squared equals to h squared plus 1 quarter. Here, we substituted those two equations from each other. That is to say, it is equation 2 minus equation 1. That is to say, it is x squared minus y squared equals to h squared plus 9 quarters minus h squared plus 1 quarter. So we have here x squared minus y squared equals to h squared plus 9 quarters minus h squared plus 1 quarter. So we open the brackets here, and I have found out that x squared minus y squared equals to h squared plus 9 quarters. We open the brackets here, we have, after we open the brackets, we have minus h squared minus 1 quarter. H squared minus h squared is 0. 9 quarters minus 1 quarters is 8 quarters. 8 quarters is 2. So in total, according to equation 3, I have found out that x squared minus y squared equals to 2. In the next step, we join points O and P together by a straight line. Point O is the center of this big semicircle. Point P is the point of the big semicircle itself. Therefore, OP is the radius of this big semicircle. This is equals to 4 units in itself, according to what we have already found out. In the next step, by copying the right triangle PSO in a new page and implemented the Pythagoras theorem on this right triangle PSO. This is right triangle PSO that I copy from the original drawing. In this right triangle PSO, PO squared, that is the square of the hypotenuse, equals to PS squared plus SO squared. PO is 4, therefore PO squared is 4 squared, that is 16, and this is equals to PS squared. PS is x, therefore PS squared is x squared plus OS squared. OS is y, therefore OS squared is y squared. So total according to equation 4, we should find out that 16 equals to x squared plus y squared. And again, according to equation 4, we already found out, just like now found out that x squared plus y squared equals to 16. But according to equation 3, we only found out that x squared minus y squared equals to 2. In the next step, we added equation 4 to equation 3. And we found out that x squared plus x squared is 2x squared, y squared minus y squared is 0, and it is equals to 16 plus 2, that is 18. So total 2x squared equals to 18. Here we divided the equation 5 by 2, and we found out that x squared equals to 18 over 2, that is 9. So according to equation 5, x squared equals to 9. Our test is to find out the size of this shaded area. The shaded area is actually this small semicircle. So we have to find out the area of this small semicircle, the shaded area. The radius of this small semicircle is x, and therefore the area of the small semicircle must be equal to pi x squared over 2. So it is pi over 2 times x squared. X squared is 9, so we sum x squared by 9. And in total, we should find out that the size of the shaded area equals to pi times 9 over 2. 9 over 2 is 4.5, so in total this expression equals to 4.5 pi. So in total, we should find out that the size of this shaded area is equals to either 4.5 pi square units inside, so in terms of numbers, the size of this shaded area equals to 14.137 square units inside. Okay, thank you very much.